Okay, good afternoon, everybody. Thank you for coming to this session of the ADA's Invited Talk. As they say, we've saved the best for the last. Self-driving vehicles are a reality of how far AI can go, and we are super thrilled to have Geoff Chi-Johnston from Cruise to give us this talk here today. He's a senior staff tech lead manager at Cruise. He supports the safety data science team, which builds algorithms for quantifying and benchmarking autonomous vehicle performance. Prior to Cruise, Geoff worked at Apple on the Apple Watch, where he helped develop the fall detection algorithm, as well as supporting other health and activity features. He's a co-inventor on multiple patent grants and applications. He received an NSF Graduate Research Fellowship, a PhD from Columbia University in Sustainable Development, and was a postdoc fellow at the Johns Hopkins University. His academic work focused on mathematical modeling of infectious diseases and evaluation of intervention strategies, including co-authored papers in Science, PNAS, and computational biology. That's quite a journey from starting in computational biology, working on Apple Watch, and now on self-driving cars. I'm also very grateful to Geoff. He flew in last night just to be here to give the talk to us today, so thank you for putting in the effort. And if you're really nice to him, you will be able to get a ride in the self-driving car. So he's very open to that. Okay, with that, please give a warm welcome to Geoff.
Thanks, Suju. I was telling Suju that she's so good at this, it might become her day job, so she should watch out. Okay, so thank you so much for this opportunity to present at the KDD conference on data science at Cruise. So for those of you who might not be as familiar, Cruise is an autonomous vehicle, or AV company, based out of San Francisco. Cruise was founded in 2013, began autonomous ride-hailing for employees in 2017, and started servicing fully driverless public fared rides in San Francisco in June 2022. And so just for background, I think we're all familiar with the promise of AVs, but I think it's fair to say AVs have the potential to improve public health as well as revolutionize many sectors of the economy. And to realize that potential, AV deployment needs to be safe, responsible, and efficient. Data science, which is an applied science with components of statistics, data engineering, computer science, and operations research, can support those goals. So in this presentation, we describe two high-level case studies applying data science at Cruise. And so let's jump in, and we'll first start with some background on autonomous vehicles, and then we'll walk through the two case studies. So for those of you who are less familiar, there are three main components of the autonomous vehicle stack, the code that runs on the autonomous vehicle. There's the perception system, the prediction system, and the planning system. So the perception system is the eyes and ears of the AV. It tells the AV what's around the AV, where is the AV, what other agents are nearby, etc. The prediction system takes inputs from the perception system and tries to predict where those neighbors, those other agents or objects will be in time and space. So how fast and in what direction are the agents traveling? And that trajectory prediction might be dependent on the type of object. So they're dependent on perception not only to know whether something is there, but what is that something? And then the planning part of the stack describes the AV's plan for how the AV will get to where it wants to go, taking into account where the other objects will be. And so there's a repeated game played out turn by turn, almost like steps in a sequence or moves on a chessboard, where you predict where agents will go, you plan where you want to be, then they react to your plan, and you react to their prediction, etc. And so you try to see if you can find the optimal, safest route to get to where you want to go, accounting for their moves. So in terms of the perception deep dive, there are multiple sensors for interpreting the world on the AV. Cameras for visual perception, radar and LiDAR for spatial and depth perception. And each sensor modality has its own strengths and limitations. Cameras, for example, might struggle to identify objects in the dark. And so if you look here at a detailed view of how each sensor perceives the world, this gives you just a little flavor of how the different sensor modalities perceive the world differently. So on the top, you can see an example of a camera's perception of the world as a 360-degree 2D visual representation. And then on the lower left-hand corner, you can see how LiDARs perceive the world as point clouds, three-dimensional point clouds, so you have depth. And then you can also see on the right an example of radar. So that gives you velocity returns both short and long range. So by fusing that information, you can get a perception of where agents are in the world, how fast they're going, and what are they. So the prediction component of the stack, which is the second component of the stack we introduced previously, attempts to answer where those different agents will be. And so that propagation of motion, the algorithms that try to compute where the agents will be are dependent on the agent type. And so the next move for a vehicle might be very different, for example, than the next move for a bicycle or a pedestrian on foot or a scooter or something like that. And as you can see in this little montage here on the right, there are many different kinds of agents in San Francisco. This is just a small enumeration. But the floor of complexity is high, so there's many different kinds of agents. So how do you bucket those agents in an intelligent way? How discrete do your buckets need to be? Those are all just questions we'll talk about in a little bit more detail. So as we mentioned, the third component is the planning stack. And the planning stack uses algorithms to move the AV to where it wants to go, accounting for the motion of the other objects. So it's where perceived and pre-mapped information comes together all at once to enable the AV's complex decision making. So on the right are 4 examples of where the AV makes a decision. So taking a gap, you can see here a gap left by the other agent, and so the AV has to decide when and how to shoot the gap that's created. Overtaking a parked car. So there's a lot of what we call double parked vehicles sort of hanging out, and you don't exactly know when they'll start or stop. And so we overtake a vehicle. Slowing for a pedestrian in a crosswalk. How do you do that in a way that's least disruptive but also optimally safe for the people walking in the crosswalk? And then how to navigate a narrow gap. That's just an illustration of 4 different scenarios. So given the proper functioning of the perception, prediction, and planning components of the AV stack, the AV could safely navigate its immediate environment. The AV can then be used to service passengers. So the next question, a higher level question, is how do you service passengers in an optimal way? What is optimal? And so the process of servicing rider demand is called routing, and it involves positioning the AVs to best satisfy demand, predicted demand, subject to a number of constraints. So in our first case study, a shorter case study of data science at Cruise, we'll describe an example of how the router optimizes over its constraints and attempts to service predicted demand. And then we'll do another longer case study after that on A/B testing and simulation. So as I just mentioned, we'll do 2 case studies. Taking a step back, data science can play many roles in AV development. So for this case study, we'll be focusing on the commercial applications. So there's a number of different applications where data science can play a role, calculating an ETA or managing the fleet where it will be pre-positioning, or on-road safety and comfort testing or simulation safety and comfort testing. So this section will talk more about the commercial routing aspects, and then in the next section we'll talk more about the simulation. So let's start our description of routing with an analogy. So if we consider AV routing in the abstract as provisioning a service across a network, consider the analogy of a power grid, which routes power from a source through power lines or nodes to demand, for example, a house or a business. So routing power along a power grid is similar in some ways to routing AVs along a road network. Both can be modeled as flows along a network with nodes and edges. So the terminology we'll use here is nodes connected by edges, connecting a source to a sink or demand. So consider what happens in this analogy to the transmission of power if a single node goes out. Depending on the network topology, that is the connectedness of the grid, the power might still be able to be serviced to the demand if the connections from source to demand are redundant. So as you can see here, this node goes out, power is still able to be routed. However, consider in our analogy what happens if a different node goes down. If other nodes are highly dependent on that node, then power might not be able to be serviced throughout the grid. So can we quantify the differential effects that some nodes have on transmission versus other nodes? So for here, because all the other nodes are highly dependent on this node, it's going to have a differential effect on transmission of power than the outage of the previous node. So how can we quantify this? So one way of quantifying this concept of how a node impacts reliability is called Betweenness Centrality. So Betweenness Centrality is defined on a graph network as the sum over every pair of nodes of the shortest number of paths between each of those pairs of nodes, which pass through a given node, divided by the number of shortest paths. So that's kind of a mouthful. Let's see how that plays out in practice. So if we look here at this example, let's calculate the betweenness centrality of node 1. So that's, if we go to the formula and we look at each pair of nodes, how often is 1 in the shortest path between those two pairs? So 2 to 4, 1 is in the shortest path, but there's also an equally short path going through 3. So there's 1 shortest path going through 1, but 2 shortest paths. So 2 and 4 would contribute 1/2 to the betweenness centrality of node 1. And actually, a bunch of nodes will contribute to the betweenness centrality of node 1. So not just 2 and 4. In fact, 2 and 5, 2 and 6, if you calculate which of these paths has 1 in the shortest path, 2 to 5 has 1 in there once, and it can also go like this. That's equally short. So 2 and 5 contribute 1/2, 2 and 6 contribute 1/2, 2 and 8, 2 and 7, 2 and 9. So if you sum those up, you actually get 3. And it's because this graph is undirected, 4 and 2 would give you another 1/2, but we count that once. So betweenness centrality tells us how important a node is to the shortest path traversal across the graph, or conversely, the negative impact from removing that node from the graph. And so using this importance score for a node, we can determine which nodes we should expand to improve overall routability, as well as identify choke points or vulnerable subgraphs. Now, unfortunately, betweenness centrality is not the only constraint that we also need to consider when routing vehicles. So betweenness centrality controls the effect of a node on routability collapse, on how reliable your network is. But there are other costs that are required to maintain node uptime. So for example, ideally, our AVs could drive everywhere equally easily, but that's not the case initially. So for example, maybe some connections are more challenging, like a roundabout or something like that, might be more challenging for the AV to navigate through. But that roundabout might have a high impact on the reliability of the network because it has a high betweenness centrality. So there's a trade-off between maintaining high reliability and high cost, which is paid in terms of like what capabilities do you need to enable to service all of the nodes in your network. And so there's probably some optimum that you could have that maximizes the reliability of your network but minimizes the number of challenging environments that you need to be exposed to or routed or into. And so we talk about these in the context of constraints that we then want to optimize over. So we built a simulation framework to optimize over those various constraints for servicing customer demand subject to connectivity, and one quantification of that is as the betweenness centrality of the nodes, and then other constraints are cost and comfort. And so we take our internal first-party data and third-party map data about the characteristics of that node, the geometry, the topology of that node, whether it's a roundabout or the curvature, things like that. You can input those as inputs into your simulation and then generate insights and metrics from how to optimize your demand subject to those constraints. All right, so that was a short case study. The next one will be a little bit more involved. And the next one we'll talk about is a deep dive on AV simulation testing. So this second case study considers how to test AV performance in a simulated environment. So specifically for the purposes of this, that's actually still a very broad topic. We'll talk about how to sketch a framework for measuring scenario realism. So a metric that measures how likely a given scenario is to occur on road. And so when you're simulating AV driving through a city, you want to know how close does your simulation mimic what you would have seen in real life. And so this metric is going to have multiple sub-metrics or dimensions like perception realism and policy realism, which we'll talk about. And then we'll talk about the benefits of simulating unrealistic scenarios and how both realistic and unrealistic scenarios can help measure and improve AV safety. So let's first talk about as a background, what are the goals of on-road and simulation AV testing? So they share the same high-level goals to measure AV safety, both relatively, release to release, so we have software that's constantly deployed out on the driving environment, and that software constantly gets updated. And we use that to measure safety one release versus the next, so relative to, from A release to B release, for example, or in absolute terms against benchmarks that we might have set for ourselves, independent benchmarks. And so how does on-road testing solve this problem? Well, on-road testing, you drive autonomous vehicles to observe your performance, and realistic settings are kind of an inbuilt advantage because you see settings at exactly the rate that they occur on road, which is pretty nice. And then you could also even invert the map to try to drive in more challenging scenarios on purpose. But there's a lot of factors that are outside of your experiment or control when you're driving on road. So for example, maybe there's a road closure or a sporting event or weather, so you can't really control the kinds of exposures your AV sees or observes. You can to some degree, but it's not perfect. Whereas in simulation, you have perfect control of what the AV sees because you design the simulation. But that's a double-edged sword because then you don't know how realistic your scenarios are. So you have to decide for yourself what kinds of scenarios you want to simulate, and are they targeted to or purposefully different than the kinds of scenarios you might have observed on road. So let's talk about a framework for measuring scenario realism. And we'll talk about some other kinds of goals for AV simulation later. But for now, let's talk about what would a realistic simulation framework look like. So let's assume we're interested in measuring our performance in a setting that would have resembled how we'd like to deploy it on the road. How do we measure that? So consider a following framework, which we'll then walk through each component of. First, we need to define the dimensions of variation, like the parameters, the embedding of this space. So we'll call that the state space. And then we're going to need to characterize the distribution or the likelihood of the variables that you're interested in measuring in this state space, the scenario likelihood. And we're going to either fill in gaps or extrapolate for long tail scenarios, things you only observe occasionally on the road. And then we're going to sample scenarios from that smooth distribution. And so you can see here, maybe there's going to be multiple dimensions in which we'll characterize the real world. And if we map those dimensions down to a lower dimensional subspace, there's probably going to be some gaps in there. And we'll have to figure out how we want to smooth those gaps out or extrapolate, and then we'll sample from the resulting distribution. So at a high level, we were a little hand-wavy in that previous slide of how we're going to map things down. So let's talk about some simplifications we may need to make. We're going to abstract away from the full complexity of on-road driving and stylize that into a simpler space, a 1 or 2D space, where we're going to characterize the kinds of behaviors that we observe. So in real life, there's a number of confounds and environmental exposures that are changing. I mean, like there's cracks in the sidewalk, there's paint that's washed away, and there's phases of the moon going on. Some of those are more or less relevant to autonomous vehicle driving. So some of these we need to abstract away to decide what are the salient or relevant dimensions along our state space that we want to characterize, and then we'll start to measure the distributions of those particular variables. So let's start by simplifying our state space into a one-dimensional state space that's like an AV on a rail. And so we're going to assume that the AV runs on a track. The agent positions are given by a set of relative distances to the AV and a series of time periods, t, and the AV can accelerate or decelerate forward, and other agents can move forward and backward. And we're going to try to characterize the probability of collisions where the bounding boxes overlap in this one-dimensional state space as a result of the inputs of the scenarios. So we're going to populate our scenario and see whether the agents collide with the AV. And so let S be the state space of the kinematics and their driving policies. So these are going to be like their speeds, positions, accelerations. And there's also going to be some kind of brain that we're going to need to give to them, a policy to decide how they're going to apply control outputs, which we'll talk about in a second. We need to define that. And that will give us everything we need to run a simulation. So let's start with 3 agents, an AV, an agent 1, and an agent 2. And let's describe our state space as a vector D, which is distances, V, velocities, A, accelerations, and F, which is the driving policies. We want to be able to map those to a probability that that particular choice of state space will result in a collision. There's a lot of other variables you could include here, but let's just, for sake of argument, start with these 4. I mean, there could be jerk, which is change of acceleration. You know, there's going to be lots of different things, especially when you move to 2 dimensions. But for now, let's just consider this as our restricted space. So the one variable we haven't defined yet is a driving policy, and that's going to be defining how the agents choose to apply control outputs based on the kinematics of themselves and the other agents. So we're going to need to even parameterize our driving policy. So a driving policy we'll call a function that takes the kinematics of the scene and maps them to a control output, which in this case is an acceleration. So like how hard will the other agents accelerate or brake based on the speeds and distances of the other agents. And that mapping will be what we call the driving policy. So if we describe all the kinematics at time t by kt, then a policy could take all the kinematics in time t and t minus 1 and t minus 2 and and on. This may vary depending on the agent, how much memory the agent has, how smart your agents are. Maybe they only react to the previous kinematics, or maybe they keep in their memory many, many periods of kinematics prior to that. Then you'll map that to an acceleration, so like half a g of acceleration forward, or a couple meters per second, or in one or the other directions. And so a very simple agent might just take only the kinematics at the given time and make a decision based on what they'll do in the next period of time, and they'll ignore all the previous time. And so if the policies are fixed and the kinematics are fixed, then that's going to uniquely determine the probability of a collision for your simulation. If in this very, very constricted world, constrained world, where we're assuming these are the only things that are going on. So what kinds of driving policies could we have? Well, driving policy could be very simple for your agents. They could be completely non-reactive, and they could just apply a constant velocity, no acceleration. They could just drive at whatever speed they had intended to drive. Now, don't be surprised if these agents collide with your AV in simulation, because they don't react to anything the AV does. But these are the simplest kind of agents you could imagine parameterizing your simulation with. Then there are other agents that are getting a little bit more sophisticated, but they're still based on rules, heuristics, that they use to decide whether and how to apply control outputs. So you could have agents who start or stop based on relatively straightforward rules, like maybe they calculate a time to collision implicitly. So that's the amount of time, if the agents projected their trajectories forward, that they would be predicted to collide. Maybe if that time to collision gets below a certain threshold, they're going to slow down because they would be predicted to collide with the AV. And then when the time to collision gets larger, they'll speed up again to their cruising velocity. So these are agents that avoid frontal collisions by, when things get too close, essentially, they just slow down. And then when things get far enough away, they start to speed up again. And avoiding rear collisions, if they're in front of the AV, maybe they're implicitly measuring how much time it takes for the AV to get to be where they just were, which is called the post-encroachment time. If that falls below a certain threshold, then they're going to accelerate and until that reaches above the threshold that they were concerned about, and then they'll maintain their cruising speed. So each of these could be parameterized relatively straightforwardly. So the avoidance of frontal collisions might be just the time to collision rate, at the threshold at which they start to brake, and then their braking force that they apply. And then the post-encroachment time, which is when the agents are coming from behind them, they could parameterize that with some threshold, and then an acceleration they choose to provide until they get maintained a safer post-encroachment time. So in this case, the policies would just be four-dimensional. I mean, that's very simplistic agent. It's only doing forward and backward. Now, obviously, we could have agents with way more than 4 parameters. You could define some controllers that have incorporate information from time periods prior to the current time period. You could even train neural networks to learn what agents should do from observed data, and that may have many, many parameters, and that may involve also time periods prior to the current one. So lots of different choices we have in our parameterization, all varying by complexity and the subsequent reactivity of the agents. There's another dimension in which the agent policies will vary. There's many dimensions, but complexity is one, and we'll talk about a second here, which is aggressiveness. So some agents may prefer to bully other agents. They will pursue their policy intents regardless of other agents' actions. Like that perfectly non-reactive agent is kind of a bully. They won't decelerate no matter what you do. They're just going to keep driving. There's 100%, if they're behind you, 100% chance of collision. That's not entirely likely to happen on road, but maybe it does happen once in a while. And so different choices of parameter settings, so for example, in those start-stop agents, we had only 4 parameters, will generate different sets of collisions that you observe in simulation, depending on how you trained your AV's behavior. And these can correspond differently to different levels of aggressiveness. So how aggressively do your agents brake? If they're in front of you, that will affect your probability of collision, and also behind, because the more aggressive they are, the less likely they are to collide with you. And vice versa, how likely and at what magnitude will they accelerate when they're in front of you? And so once a parameterization's been assumed, you could just sweep through those parameters and generate a whole bunch of simulations to observe the rates at which your AV gets into uncomfortable situations. But you can also fit them to data. So we'll talk about how we fit them to data in a second. And so let's assume that the kinematic features in the agent policies defined above describe the scenario dimensions, and only those parameters. How can we sample realistic scenarios from that restricted space? So there's going to be many different variations here of realism, even with this restricted space. So let's talk first about how we parameterize the initial constraints of the simulation. And then we'll talk first about how we parameterize the evolving dynamics of the situation. So how do we decide what agents get to be populated where to start our simulations, for example? So in real-world driving, agents enter from any direction. So maybe you're getting a cut-in from behind, maybe you're getting a cut-in from the front, maybe a fake cut-in, so somebody pretends to cut in, then decides not to cut in. You could embed those 2D trajectories in your 1D simulation by varying the distribution of where they started, the relative distances. There's going to be some distribution, some implicit distribution you could get from embedding lots of two-dimensional interactions in this 1D on a rails simulation. So for example, the cut-in, you might have some distribution of when agents decide to cut in. Maybe they cut in front of you more often than they do behind. And then you'll have right-turning agents. For example, some agents may feint or fake a right turn. Other agents may actually make a right turn. And other agents may just simply go straight, even though they were intending, you had thought they would be intending to take a right turn. Or maybe that the traffic laws stipulated that they take a right turn. So for example, as you can see here, here is a set of trajectories from observed driving in San Francisco. So this is empirical data that one could use to characterize the starting kinematics likelihoods of your simulations. So all the agents entering your simulation start with different velocities and accelerations, and they eventually take different paths through your simulation, but these paths themselves would be simulated based on the dynamics, but at least you'd be able to start your parameterization with the observed dynamics that you happen to have seen empirically when driving around the city. And that distribution, so maybe vehicles and bicycles have different distributions of how they enter into your left-hand turn simulation, for example, or maybe emergency medical vehicles, they have a different distribution. And it's going to depend on the traffic controls. So whether there's turning signals or signage, if there's a stoplight here, there may be a different distribution, or a pedestrian crossway. And the maneuver type will also determine that as well. So when you're turning left, the distributions of agents, and they'll enter your simulation from both directions. There'll be oncomers as well as trailers. Will vary versus if you had just been on a straightaway. And so these are some, as a sort of a snapshot of some of those trajectories. So let's talk about another confound that will affect how you parameterize the starting positions and kinematics of your agents, is perception realism. So we talked earlier that one of the components of the AV stack is the perception system, and it uses different sensor modalities to perceive the world. Well, those sensor modalities have different ranges, and they operate with different performance levels in different environments, at night, for example. And so the starting locations of your agents are not determined by their actual on-road locations, but by when the AV perceives them, because that's when, for all intents and purposes, they first interact. And if that's very late in the process, because of one reason or another, as we'll see, then that makes it more challenging. But you want to simulate at exactly the same challenge you might be expected to observe on road. And so, if there's weather, or if the object type based on the size of the agent or the type of the agent varies, or the levels of occlusion vary, then you want to capture those same rates of perception artifacts in your simulation. So for example, let's say that you had a car that's immediately adjacent to you, a large car, and that occludes your line of sight. You might only observe these agents entering your simulation far into the process of their cut-in. So when they emerge is already at a relatively low relative distance. Or here, if you had a car in front of you, you may not observe this car cutting in until relatively late in the game. But you want to simulate that at exactly the same rate as you observe on the road, because these kinds of events happen. And so you want to make sure you're capturing your parameterizations in a realistic way. Not that you would see every single car as far ahead in advance as you would theoretically be able to, but realistically be able to. So let's see here an example of emerging agents on a narrow road with blind turns. You'll see two examples, actually, of agents that emerge quite late in the game. There's one agent there, and then there's going to be another agent that's going to come up because you have lots of blind turns, relatively late because of an occlusion and a blind turn. So this agent right there. You can see they were both occluded by that sprinter van, and it was a blind turn. So you don't observe them until they're relatively close to you. And so when you parameterize your simulation, you want to make sure you parameterize it with those agents as they occur on the road, the same distribution. That's perception realism. Let's see it come around the bend here one more time. There it is. Okay. So let's talk about another dimension that we want to ensure realism across. So we'll call policy realism. So recall that we parameterized our policies. We had many choices of policy parameterizations, and they varied in terms of levels of implicit or aggressiveness. So we want to sample scenarios with agent policies that also match the observed on-road distributions of aggressiveness or reactivity. So let's consider a bunch of observed interactions between the AV and other agents. So what you see on the right here is the post-encroachment time. That's the number of seconds between when the agent behind occupies the same cell as the AV did previously. So if the post-encroachment time is 1 second, it takes 1 second for the agent to be where the AV was. If it's 2 seconds, it takes 2 seconds for the agent to be where the AV was. And the shorter those get, the closer the agents are. And so if you see some of these trends, you could imagine what's going on here is, let's say the AV stops or the other agent accelerates, and the post-encroachment time gets small. So that means they're quite close to the AV. They're quite nearby the rear of the AV. The PET gets low. And then either if the AV was stopping, they stop and the PET goes back up, or if the AV was accelerating, they slow down. Or there's a few different ways that you can see this come up, depending on if the AV accelerates or if they slow down. But anyway, so there will be trajectories where you see here where there's this parabolic shape. And that parabolic shape encodes some information about when do they start reacting and how hard do they react. And that's also a function of how hard, not depicted here, is also a function of how hard did the AV react. How hard did the AV stop initially maybe, or how hard did the AV accelerate to increase the gap speed. And so you could parameterize your simulations, some of those relatively straightforward agents, directly from data like this. Or if you trained a neural network, it will implicitly learn to model behavior like this, although it's doing lots of other things at the same time. But it's still implicitly learning these kinds of distributions and reactions. And so if you wanted to characterize the performance of your agents as modeling realistic behaviors, you could measure a number of characteristics from these kinds of distributions, like the 5th percentile average, 95th percentile of these. And then if you looked at the actual physical distances, how far do people give you in terms of average leeway? If you parameterize this first initial drop as a reaction time, or when the curve started to move back up to its equilibrium point, how quickly did that reaction occur, either by the AV or the agent? And so these are all ways you could sort of gather information from these curves and distributions and see how well your simulations fit to those data. And so another set of metrics, that's not the only set of metrics you might want to measure, so that measures aggressiveness or reactivity. Another way to sample realistic scenarios depends on the maneuver type. So now we're moving a little bit away from the one-dimensional example into some of the complexities you would see with the two-dimensional example. And so, for example, if the AV was taking a left turn and you saw agents taking left turns behind the AV, you could measure the average rate of curvature or the different percentiles of curvature or even a distributional fit of the curvature or the integrated distance. And so you can measure how realistic are your agent's turns relative to the turns you observed. Are they pulling the same amount of normal force or centripetal force as the agents you observed? Are they pulling less or more, or is even the distribution tighter than you observed? Like there's more variation on road than in your simulation. And so those distributions of turns will be dependent, as we said, on agent type, the traffic controls, the maneuver, the position, the velocity, and also what the AV was doing. So these are kind of pairs of joint trajectories. So we'll see that in order to characterize this distribution, you're going to have to characterize both what the AV and the other agent were implicitly doing, and then you'll measure these various metrics and then see how well your simulation is calibrated to those. So as I said, one of the challenges when you move from one dimension to two dimensions is that you have multiple branches of potential reactions between an agent and an AV. And if you call an agent AV as a policy maneuver pair, that joint distribution, you're going to, let's say you assume that you were taking a left turn and you're assuming your agent was also intending to take a left turn, and let's say that it was unprotected, then based on the taxonomy that you derive or that you decide using mechanistic or first principles arguments, maybe it's even machine learned, you'll then be able to characterize whether your agents were behaved illegally or legally but aggressive or realistic or conservative within that particular set of scenarios, within that joint pair, within that branch of the tree. And so this is almost like a grammar of human behavior. So those other plots will be, you'll have sort of plots for each one of these different branches, and you'll characterize the aggressiveness and distributions for each one of these, the joint policy scenarios. So assuming you have this taxonomy, and assuming you're able to characterize the joint likelihood, what is aggressive in each of these contexts, you'll be able to then ensure you have realistic scenario coverage if realism is your goal. And then you could measure your safety rates, your probability of collision, on each of those realistic scenarios. And then you could estimate your overall safety rate by just taking the weighted average of each of the safety rates within each of these branches and aggregating up based on some weighted average on the likelihood of seeing these scenarios in the first place. And so the challenge with the realistic sampling is that there are advantages to non-realistic sampling. So for example, you might not want to just sample in a realistic way because there's going to be high cost. You're going to be sampling lots of scenarios where there's not much going on, where it's relatively safe. And so you could also imagine, implicitly you'll be seeing very few of these long tail events, the ones you may be especially interested in. So another way to sample would just be to sample long tail events, adversarial events, agents that you think are being willfully aggressive, willfully non-reactive, moving at a very high rate, under high occlusion, all sorts of challenging circumstances and scenarios. And so it depends on the purpose of the scenarios. And so if we look here at an example of some learned agents that were trained to be adversarial, you can see on the left, these agents are behaving normally, quite nominally. They're not intending to collide. And then as we move through this process of training to become more and more adversarial, you'll see them more and more likely to cause a collision. So if you see this one again, on the right, you'll see the agents that are trained with greater and greater likelihood to try to cause a collision. And this one caused the collision really quickly in the simulation because it kind of just cut over right into the AV. And so you can generate scenarios like this, but how realistic is this? How likely is this to occur on road? It probably does occur once in a while, but what is once in a while, and how do you calibrate that in terms of a risk? So the overall goal then would be to combine approaches for being able to sample in a realistic or representative way using the scenario realism framework, and then also leverage some of these adversarial tools, which will be able to allow you to sample from the long tail of highly challenging or aggressive agents. Can you sample realistically aggressive agents? Agents that are aggressive in exactly the same way you would have observed on the road, but are still challenging, that you could still be able to contextualize in a likelihood of having seen those or observed those kinds of agents on road. So that's one of the challenges, and to see if you can be able to take a so what or a TLDR from these types of agents and to be able to put them into a context and say, well, this means that we can stack rank these kinds of challenging scenarios and know which ones we want to solve first, because you know which ones are more likely to actually occur. So how does data science contribute to this overall effort? So many of the individual components of these simulation frameworks are the focus of domain expert teams. So planning and controls or robotics or AI teams develop driving policies for agents, and that could be based on black box approaches or maybe more traditional controls-based approaches. And prediction teams generate predictions for future agent trajectories, and perception teams generate which tracks and when they'll be perceived in the agent's AV's field of view. So data science can help structure the end-to-end interpretation of these simulations, the so what, and characterize those by measuring what is important in terms of the end-to-end performance and validation. Not that those other teams wouldn't do that, but maybe that's one of the natural use cases for data science or applications of data science. So there's a lot of open questions here still to be solved. So what's a minimal useful parameterization for simulations, including driving policies? Do you need a neural network? Can we ensure coverage of long-tail events, but also understand how likely those long-tail events are to actually occur, not only to generate them? How can you optimize your on-road mileage accumulation to sample these kinds of scenarios? On-road mileage accumulation is extremely expensive. It's very difficult to maintain and highly costly to maintain a fleet of autonomous vehicles driving around in real-world scenarios. How can we sample simulations to represent locations where we've accumulated little or no mileage? How do you know what the driver behaviors are going to be like? What kinds of occlusion could be present? What types of metrics can be used to measure safety beyond collisions? We just talked here about probability of collisions, but there's probably lots of other metrics you could be measuring from these kinds of simulations. So these are the kinds of questions that we're actively exploring. If they sound interesting, please reach out, and we'd be happy to discuss further. And then maybe this is a little bit of self-backslapping or celebration, but just wanted to end on a milestone, a recent milestone that we had where we deployed a driverless rideshare service in SF. It's fully driverless. People are paying fares. It's only in the night, but nevertheless, it's a pretty big milestone because it's a commercial service that's actually servicing real people. So that just rolled out in June, a couple months ago in San Francisco. So I'd like to open it up for any questions, and thank you so much.
Hey, thanks so much. This is really cool. I was wondering, especially in the simulation fitting thing, a lot of the parameterization, I think, can be your policy dependent. So you might observe different behaviors from other agents depending on what your policy was. How do you guys loop back in your policy into how do you parameterize other agents' behavior? That's
a great question. Exactly like you said, it's a joint distribution, right? So what is aggressive to you might depend on how aggressive you are.
Sure.
And how much, I don't want to be too specific, but exactly like you saw that you could fan out other agents' choices, you could imagine fanning out your own choices and trying to find an optimum there that is safest but still effective at delivering people to where they need to go.
I imagine though that's when you're expanding the parameter space so much that getting on-road coverage becomes quite difficult because now you have to vastly sample. You have to sample over your own policies, drawing intersection with their policy too.
Exactly. So maybe one of the things you could do there is collect information from the scenarios that you're looking to on road. So by targeted data collection, if you're looking for particular scenarios that you think might be especially challenging.
Right. Try to figure out like how much to cut somebody off before you induce road rage or something. Yeah.
Thanks for a great talk. Question for you is about simulation and sort of the real life performance. Is there a way that you guys measure in terms of how complex my simulation gets and how much improvement I'm getting in real world scenarios? I know it's a difficult thing to measure, but I'm just wondering on this iteration of improving simulation and making it more realistic, whether it's for scenarios, the scenes, or the actual agent behaviors, ultimately you just want to drive better, right? So yeah, I'm trying to understand how do you measure improvements in simulation that are actually helping your real world scenarios?
Yeah, so the correlation between simulated and on-road metrics is a super challenging task. I think I was just actually, for one reason or another, flipping in my phone, looking at some pictures I had taken a couple years ago, and it was like on a whiteboard. It's like, how do we, how can we improve our correlation between? I mean, it's still something we're working on. So I think it does happen where, in simulation you would predict. So first off, you first want to establish that any given change that you make is safer in simulation, right? That's going to be a necessary, but maybe not a sufficient condition. Because if you assume that the agents are acting the ways that you think that they're acting, then the behavior that you now chose to implement should generally be safer in simulation. But exactly like you said, maybe what if it happens to be the case that it doesn't play out that way in the real world? That's exactly why you want to rely on frameworks like this, because you want to go back and then debug, okay, well, what was it about our simulation that predicted agent behavior differently than they happen to do in the real world? Was that because we hadn't seen those kinds of agents before? Was that just by random chance that we just happened to get unlucky with an agent that was super adversarial or highly unreactive? Or was it something that we did that stimulated their behavior? I think it's still an ongoing open area.
Okay, just one follow-up. In terms of actual performance in real-world driving, what are some of the metrics we're saying we're doing well or we're not doing well?
I can't go into too much detail, but I'll say that we use more metrics than just like the number of collisions. There's lots of different kinds of metrics you can imagine. Some sort of like alluded to in there that you could measure the distributions of on road and see if those are improving over time.
Thank you.
Thanks for the talk. Seeing the footage in San Francisco, it got me very curious how challenging it might be to take into account stuff that's unique to San Francisco, like how steep the roads can affect perception, and if, for instance, if you have to treat streetcars as a separate type of agent.
Yeah, for sure. The idiosyncrasies in San Francisco present a lot of challenges. I'd say taking a step back, I think that was an insight that some of the early founders at Cruise had, was that you want to start in the places that are the most challenging, exactly for that reason. Because even if you demonstrated a proof of concept in a simpler area, it might not translate as easily to an area where, exactly like you said, maybe there's a lot of occlusions because of hills, or maybe there's like the public transportation system presents particular challenges, or maybe the drivers are more aggressive, or they're more aggressive pedestrians or something like that. So I think the overall perspective is that by testing in San Francisco, where you see lots and lots of different kinds of challenges, you'll be able to accelerate your learning. But that being said, in San Francisco, there are kinds of challenges we probably haven't been exposed to as much, like driving on ice or driving in a thunderstorm. And I think those are probably still open challenges.
The way you answered that, I'm very tempted to ask a very quick follow-up. Have you kind of tested that theory that if you start in a challenging environment that it's easier later, like have you test driven in Oakland or something where perhaps it's not as hilly and you don't have the streetcars?
I think we're also testing in Phoenix.
Oh, I see. Okay. Thank you.
That's a great question. Just so for everyone's benefit, Suju asked, when is the simulation good enough so you feel like you don't need to do any more on-road data collection? I'll be completely honest, I'm not sure yet. That's kind of one of the questions that this line of work is trying to answer. I guess you could measure the rate of surprisals that you see on the road. So how often does something happen, or how often does an agent appear that does something different than you expected? And if you're driving that rate down, that might over time give you some confidence. So maybe you could project that rate and look to see if your rate of surprisals is decreasing, and then over time, when do you think that the rate of surprisals will be low enough that you're able to satisfy some kind of internal benchmark for quality?
I was in the restroom for a couple of minutes. Did you talk about the type of model you're using? Are you able to?
So we talked about it in like at a high level. There are different kinds of models. So there's like different levels of parameterization. You could parameterize models where the agents have explicit intents, and each of the parameters corresponds to an intent. Like if the time to collision goes below a certain threshold, the agent might react by slowing down, for example. And there's like a cause and effect relationship.
Yeah,
Or
no,
you
I
could
meant like, are you using neural networks?
Yeah, I was about to say,
Okay.
you could also train kinds of models where there's a less clear one-to-one correspondence between the model parameters and the resulting actions. The challenge for those models then is you might still want to be able to back out what was the relationship between the trained parameters and how reactive were the agents. So you still may need to do some of that work after the fact.
How about robustness, right? So, I mean, simulation and so on, I mean, you can test, let's say if you would take out one of the sensors and so on, how much overlap is there in terms of robustness if something goes wrong, right? So how much everything gets worse, right?
That's right. Exactly like you saw here with the perception realism, that's related to the idea of that some of your sensors might be off if they're highly occluded. Or like different sensors are affected differentially by, for example, weather. And so I think my impression is we're pretty careful about only operating in areas where we think that our performance is above the threshold we currently expect. And so we don't operate on extremely foggy nights, for example, currently. But over time, you would hope that the envelope of feasibility would start to increase as you're either able to leverage other sensors more, rely on other sensors that are less affected by that particular issue, or leverage the data that you do get by filtering intelligently so that you're able to still operate using that one sensor.
And maybe one more question. So the scenarios which you were showing, right? So when a car drives through among other cars and so on, so do you estimate what's the, because there's always some non-zero probability that actually there's a chance of crash, right? I mean, it's very simple, right? So are you maintaining this probability in one or the other way? Because you cannot control the whole situation, right? And many events can happen where you don't know. How do you deal with this?
Yeah, so I think, so just taking a step back, I don't think that when autonomous vehicles are deployed that there won't be any crashes. I think maybe one of the goals is that there are fewer crashes. So like you said, if an agent just decides that they're going to be hell-bent on crashing into you, it may not be anything for you to be able to do there. But does the rate of those kinds of occurrences, is that lower than what's the status quo on the roads now? So that's definitely a reference point we use when gauging the readiness of the technology is what's happening out on the roads. And I don't want to be too specific, but I think it's fair to say that we do look at that and look to see how we compare it at a high level.
Yeah, because the sensitivity of people, right, is so much higher towards this kind of crashes, right? That's why I was asking, yeah.